Good evening, everybody, and welcome once again to the Mexborough and Swinton's Zoominar, or even webinar. I'm just going through now with Lawrence's introduction. He started his interest in astronomy at a young age by admiring how pretty the night sky is, assuming no clouds and low light pollution. Luckily, he obtained his first proper telescope at 14 with a Meade LX90 Matsutov Cassegrain, and he observed heavily on cold nights the ethereal M31, the majestic M42, and the sisters of M45, as well as many other objects. After starting the wrong degree course at the wrong university, that says a lot, Lawrence, I'm afraid. He ended up studying physics and astronomy courses properly with the Open University, graduating his Bachelor of Science in 2014. He then moved to their home campus at Milton Keynes for a research master's focusing on the study of active galactic nuclei and one of the more power objects in the universe, graduating in 2016. Finally, this landed him with a PhD position within the E.A. Milne Centre for Astrophysics at the University of Hull, where his recent works have involved probing the dynamical effects of large-scale structures, such as galaxy clusters, as galaxy clusters have on the very cluster galaxies that form their structure. He's currently in the process of submitting his PhD thesis for examination, after which he hopes to continue his work. So please can we give him a welcome to this evening's webinar.
Thank you, everyone. Right, can people see that?
Yes, large-scale structures in the universe, the hierarchy of nature.
Awesome. Right, well, I must say, thank you very much for that introduction, Steve. And I must apologise for the lateness of my arrival, sorry. And for the not being able to make the last one. I was quite ill, unfortunately. So yeah, thanks for that introduction, Steve. I don't need to introduce myself, I don't think, anymore. All I'll say is that I've now finished my studies. I've now passed my PhD, so I'm now hopefully moving on to the next level there. It's a great shame I can't be there with you this evening, thanks to features outside of our control, but we've got the wonders of the internet, so hopefully I can take you on a very leisurely stroll on this talk tonight through one of the more, I guess, untouched topics of astronomy, I'd say. And I must apologize, I think one or two of my peers might have already covered one or two things, maybe. There's some crossover, but hopefully you don't mind hearing it again. And it won't be too boring, and it's somewhat entertaining for you. So, with that in mind, start with a bit of history. If I move on to the next slide, there we go. So, one or two, or a few, or all of you may be familiar with something that was called the Great Debate. Now, as with everything, it seems in astronomy, we like to make a grand gesture or make a grand statement. It's like, it has to be not just a debate on something, it has to be a great debate. Now, in the middle, or sorry, not in the middle, in the start of the 20th century, there was a sort of impasse or a crossroads in understanding the actual true nature and scale and size of the universe. There were many opposing philosophies and ideas about our place in the universe. And this culminated on the 26th of April, 1920. Two prominent astronomers at the time, you've got Harlow Shapley on the left there, pictured on the left, and Heber Curtis on the right. And they sat in two camps in what they believed to be the actual true scale of the universe. So Harlow believed that the entire universe was the Milky Way, and nothing was beyond that. Everything was contained nice and neatly in what we described as the Milky Way, and that was that. So everything was relatively, I say relatively nearby. He believed it was about only 30,000 light years or so in size. On the other side, you have Curtis, who believed in what was prescribed as an island universe model, which was first postulated by Immanuel Kant a few hundred years before, 100 years prior. And that, which is quite interesting because he wasn't really an astronomer himself, but he was interested nonetheless. Yeah, so there was these two somewhat opposing views, and they during this congregation of astronomers, it wasn't just them two, of course. There's many prominent people in the field. They brought together their arguments, and they both had fairly compelling arguments on either side at the time. Harlow also had other people backing him as well. So, for example, you had the Dutch-American astronomer Adrian van Manen actually provided some observational evidence to support his view in the M101 Pinwheel galaxy. He actually performed observations that were 10 or 20 years apart, and he believed from his observational evidence that it showed that some rotation was occurring in the galaxy, and if that was indeed the case, then the M101 nebulae, as these objects were referred to as spiral nebulae at the time, curious objects that were what led to this debate, believed to be rotating. If it was rotating, it must be relatively nearby, because it was known that light had a finite limit in speed, and therefore there must be, if it was relatively nearby and you could see it rotating, it must be close. However, despite that eagerness to prove that side of things, it was turned out that Adrian actually performed an error in his measurements, probably due to the psyche, of wanting to find something to prove what you already believe in. Maybe, I'm not sure, but he was using what's called a stereo blink comparator. So it's like a microscope almost kind of thing, and it allows you to compare two plates very quickly. And his reference stars, they changed, distance from 10 to 20 years ago to his observations that he made recently. But because they were so edged to the plate, it was spurious. There was edge effects on the plate. It was not actually correctly imprinted, and that led to an erroneous result, which was later confirmed by other astronomers that it wasn't true. And it was, again, sort of showed to be the case later. There were also other things as well that was postulated. Curtis actually asked if it was indeed the case that galaxies like Andromeda were in the Milky Way, why would we see such a large concentration of novae in such a small volume of the sky? And Harlow argued that you can't have such luminous objects at such a great distance. That would imply something incredibly powerful happening. Of course, this was before supernovae were fully understood or known about properly back then. But it was obviously shown, if you modeled this, if you actually extrapolate that those novae in Andromeda, if you expand it to the size of scales that are extragalactic, i.e. beyond 30,000 light years, it actually works out to being the same distribution as the Milky Way. So there was lots of toing and froing, and there was nothing really conclusive that came out actually at the debate at the time. So that leads us nicely on to another prominent figure that everyone here will no doubt know, Edwin Powell Hubble. He was, it's pretty, actually, if you don't mind me going on a tangent a little bit, kind of interesting chap, because he started his career studying law. Law and astronomy are not really the same thing, but I guess he was doing it to obey his father's wishes, because he was very dutiful, and his father wished him to study law. But this is despite his keen interest as a child to really want to study astronomy. So while studying for his law degree, he did do a few courses here and there in science and maths and such. The US system allows you to do that. However, it wasn't really until his father's passing in 1913 that he became quite disinterested in actually practicing law. And in between that and teaching at high school, he enrolled into a PhD at the University of Chicago, Yerkes Observatory, and managed to enroll himself onto a PhD there. Despite his very limited background knowledge, he managed to work his way up because he's shown he was capable. So yes, he started his PhD, and 1917, he rushed to get it done, his PhD thesis, because he wanted to sign up to go to war in the First World War. As when the US declared war on Germany in 1917, he signed up and enlisted. But once the war had ended, Hubble stayed in Europe actually. Specifically, he went to the University of Cambridge for a year before finally taking up a position in 1919 at Mount Wilson Observatory near Pasadena, where he would famously use the Hooker telescope, that 100-inch refractor, 2.5 meter telescope, where he would then observe and calculate distances to M31 and M33, spiral elliptical nebulae, still obviously not known where, the true scale at the time. And they used Cepheid variable stars, and Cepheid variables, if you do or do not know, they are what's called a standard candle. And the great thing about using Cepheid variables is it was discovered that there is a strong relationship between their luminosity, their brightness, and the pulsation of these stars. There's a variability in their luminosity and their brightness, and the time between these pulsations is very strongly dependent upon their luminosity and brightness. And when you model this, you can then determine the distance to these stars with a very good approximation. So when Hubble did this, he realized that in M31 and M33, that these stars are not local. They seem to represent within the nebulae that we're in, the spiral elliptical nebulae that we're in, that they were their own island universes, to coin Immanuel Kant's terminology there. So that the whole idea of everything being less than 30,000 light years seems to be dead by this point, blowing everyone's viewpoint wide open. And then later on, Hubble very famously used the same methodology to do a variety of different systems, and discovered his Hubble's law, or the Hubble flow, in which as you increase in your distance of these extragalactic objects, the further, or so the faster they're traveling away from us. So he found that space itself seems to be expanding. Excuse me. So now we have our universe. It's no longer as localized as we thought. And so this is like a visualization of what our galaxy could be like. We don't know for sure because we're in the galaxy itself. It's not hard to know the actual precise structuring. We can make inferences and guesses. So this is one representation. And if you can't see, we're supposed to be here in the Orion spur, just breaking off the main arm there. Very far, yeah, well, when you consider the actual size of the rest of the universe, it's amazing how isolated it seems and how small we seem in this context. So yeah, the Milky Way, home to our star, but even though it seems apparently isolated, this island universe of gas, dust, and stars, it's also hosting a supermassive black hole in the center. Isolated it is not. There's actually neighbors and friends now that are not encapsulated into one island, but multiple. So we've got our local neighborhood. This is what we'd call our local group. If you can see my cursor at all, probably not. But it's a million light years scale there, as you can see. And we are here, the Milky Way is in the center there. And this is, so you've got Andromeda just to the right there, and then Triangular and loads of little dwarfs hanging around. And this is the local space around the other nearby local island-ish universes, along with a lot of smaller ones that make up such a small amount of mass, really, in such a large volume when you think about it. Doesn't end here. It keeps on going. So if we move on out, we can then see that the local group is sort of a part of a filament which is heading towards the Virgo cluster, which is here. This is technically the region that our group is a part of. And there's also the Fornax cluster down here, the next nearest cluster, and one that is heavily studied by astronomers actually for many case studies. And there we are in the center again of that rest frame. So we're now zooming out, and already space is getting bigger, dots are getting smaller. But perhaps there's a pattern forming. Perhaps you can notice things are clumping together into certain regions. Perhaps structures are forming. So this moves on to another prominent, I guess all these guys are prominent really, if I ever talk about anyone in particular. But this is George Abel. He was actually, he had a very traditional background in terms of his career, astronomy career. He studied at Caltech throughout his entire studious life, so from his bachelor's to his master's to his PhD. And he was also a student of Donald Osterbrook, which was a very, very famous, prominent astronomer at the time. And eventually successfully completed his PhD in 1957, and immediately got work onto got onto working one of the first key all sky surveys. He was at the Palomar Sky Survey, which used the Samuel Ocean telescope, which is a 48-inch sort of reflector. And the Palomar Observatory All Sky Survey was, I think, about the second or third All Sky Survey, and it was meant to be a continuation on from one of the first ones, which was conducted by Walter Bader and Fritz Zwicky, using an 18-inch Schmidt. Quite some time ago, and back then, actually, when they first did that, it wasn't even thought of to do an all-sky survey. It was actually Zwicky's idea, I believe, because he came with a lot of novel ideas at the time. But the program itself, it surveyed 3/4 of the sky, which is pretty big, and it garnered a representative population of sample stars, galaxies, large-scale structures, and this was done in different colors, different filters, on photographic plates, back in the old days of using plates, not using CCDs. And this ultimately resulted in his famous catalogue of galaxy clusters, of which over 2,712 galaxy clusters were accumulated, and a lot of people at the time said this represents a supreme effort and work to the astronomical community. He really slogged at this. This was not an easy task to define over nearly 3,000 galaxy clusters by hand, and with this it came. He also discovered that there was not only of these galaxy cluster structures made up of large volumes of galaxies. It also helped to disprove the Charlier cosmological model, which believes that basically as you increase if you zoom out further from our central point of looking at the Milky Way to greater scales, he hypothesized it should fizzle out, so the density should decrease, there should be less structure. But that appears to be the opposite case, thanks to George Abel's work. Unfortunately, he passed away prematurely before being able to finish the rest of the catalogue, because there was a Southern Hemisphere component which added about 2,000 more galaxy clusters. So it was done posthumously. But this leads on nicely to the building blocks of what we now know as galaxy clusters. Like concretely, George Abel kind of formulated the package needed to allow us to continue working and studying these objects now. So, clusters of galaxies, how do they form? Well, the very simple answer is, I guess, probably unexpected for most of you here, maybe, is that they form by gravity. Gravity pulls these things together, as does most things at this scale, you know. So the interesting thing is how these objects form, because it seems a bit strange to think, oh, you've got these galaxies, and how if all these galaxies are forming in a uniformly in a strip from gas clouds collapsing, then how do you get them to clump together to form these bigger structures? And it appears that from observation and from modeling, when we look at these, is that if you have two independent filaments coming close, just expanding in a flow, and they meet, they'll harass each other enough where they'll converge on confluence, and they'll begin to collapse on one another. So two independent filaments of galaxies, so it's just these little strings of galaxies where they formed, they end up collapsing inwards. And yeah, so this leads to a continuation of this, that once you gain enough mass, enough strong enough gravity, it will continue to harass passing by galaxies and help build its mass even greater to a greater one, and even become a bigger size. So that's how they assemble and accumulate over time. Starts off small through an initial filament collapse, and then you build that mass to a greater level, a greater scale. Yep, and starts its infall journey to the center of the gravitational potential well, which is the center of all gravity in this case. This is a nice little video, if it plays well, of the Millennium simulation illustrating this. So you've got the galaxies sort of coalescing into filaments, and then eventually they'll converge and they sort of collapse into the center. It stops there. Pretty cool little thing, that. Right, so clusters of galaxies, they don't just contain the galaxies, there's much more to them than that, more than meets the eye. Thanks to observing in multiple bands and building up knowledge over the decades. So you've got the galaxies for sure, as the obvious one, but you've also got there's a hot gas and plasma, extremely hot, that pervades the region between the galaxies. And also you've got dark matter, which everyone will have definitely heard of. Now, interestingly, well, not interestingly, if you're already familiar with dark matter's involvement in most things, the galaxies only really make 1% of the total mass fraction of a galaxy cluster. The other 9% is the intercluster medium, that gas in between, hot gas, hot plasma, and then the rest is the dark matter, which gives us the bulk of the gravity. So some other interesting cool facts about galaxy clusters. Membership of these things can be in the thousands. George Abel defined galaxy clusters to be anything greater than 50 in number, within a certain magnitude, certain brightness limit, within a certain radius. But these things can go quite big. Like the biggest example is the Coma cluster. It's one of the nearby most well-assembled galaxy clusters. It contains about just over 1,000 galaxies on its own. So 1,000 Milky Ways, if you want to put it that way, it's quite incredible to think about, especially if you want to put into context how many other potential Earths there could be in there. These things are very heavy, 10 to 14, 10 to 15 solar masses. So I don't know if people are familiar with scientific notation or not, but it's just 1 with about 14 zeros or 15 zeros after it, times the mass of the sun. Very heavy. and they can be very large. So their effects can be felt probably up to 10 megaparsecs away, which is about 30 million light years. Or I guess you could say like a 10 or 100 billion kilometers or something like that. So yeah, the effects of these galaxy clusters can be felt to quite a large distance, although the main bulk of a cluster would be probably a tenth of that, probably about close to a megaparsec to 2 megaparsecs in size. That's where most of the galaxies, most interaction occurs. But the distribution of mass across these galaxy clusters is roughly the same across the board. So they're all fairly uniform objects of structure. So there are notable mentions. So I don't know how many people are familiar with things like the bullet cluster, but essentially what this is a merger between, beg my pardon, a small and a large cluster. A small cluster is basically on zooming really fast, and it's gone straight through the bigger cluster and it's come out the other side. And the bow shock, the leading edge of the smaller cluster entering through the larger cluster, has created a wake behind it and a bow shock at the front. So it's a pretty cool looking image that this gives us. This is the Chandra X-ray telescope, and this is the intracluster medium, that hot gas plasma I told you about, pervading the space in between the galaxies. This is the resulting interactions with the hot gas interacting with itself, or the other ICM, or the intracluster medium of the other galaxy cluster. And you see this here, it's very bright. So the white bit is the hottest part, if you want to put it that way. Yeah, I've just said that in words already. If you look at this composite though, this is an optical overlay with the Chandra emission in the red, and the calculated lensing effects, gravitational lensing effects. I'm not going to go to great detail about gravitational lensing, but when you have a heavy object, light is bent around it because the mass is strong enough to be able to basically bend the light around. It's one of Einstein's greatest parts of general relativity. And the lensing effect is shaded in like a blue on either side of the little red bits, which is the intracluster medium. And the interesting thing is that the lensing effects are dissociated, they're disconnected from the intracluster medium in the red, and the intracluster medium itself is trailing behind the actual galaxies of the smaller cluster. So I keep using my finger, but I forget I'm using a computer screen. So here you've got a collection, this is the smaller galaxy cluster, and it's lensing as well. But this is ahead of the pervading ICM intracluster medium, which is meant to be sort of a part of the cluster. It's been pulled back. So the galaxies themselves are, because the galaxies are very lower in number compared to the number of particles in the hot gas, they don't interact as much. They're less likely to collide with other things. And as a result, they're just following a higher mass. So in other words, they are concentrating themselves on the dark matter concentration. So this can be seen, oops, I didn't mean to do that. This can be seen as the best evidence yet for dark matter, purely because the galaxies themselves are not, they're following the main bulk of the mass, and the main bulk of the mass is invisible. And it's this invisible dark matter, rather than following the ICM. So that is a very interesting point from this image alone. So we've got our galaxy clusters. They don't stop there. There's a higher order of structure, which is, as I mentioned, George Abel discovered these supercluster structures, which disproved Charles Charlier's hypothesis that it decreases in density as you increase outwards. And yeah, this is where we're at now. This is the supercluster sort of scales of 100 million light years. Virgo is here. We are about here. There we are. And now, basically, the Milky Way is lost. The sun is lost. If you can, finding a needle in a haystack, if you can find the sun in that, it's a challenge. I dare you to try and find it. So there are many larger structures here, and now you can start to see this structure taking shape. There's all sorts of things going around, connecting in a seemingly sort of pseudo-ordered fashion, with space in between, which I'll go on to in a bit shortly. So the universe is a hierarchy of structure, essentially. So observing these large scales is kind of interesting, though. When it's awesome to put it in that 3D context, but how we see it as observers is very different. So we observe it by doing redshift galaxy surveys, essentially. So we observe all these galaxies in the night sky, and we measure the cosmological effects, the Hubble expansion distances, redshifts to these galaxies, and we do it in slices across the sky. So you'll find here you've got this axis will be your redshift, so this is increasing in your distance based upon the cosmological expansion of space, and then you've got your separation in the sky in right ascension purely. So it's a 4-degree slice, and there's 63,000 galaxies in this, as it says in the caption underneath. And this is specifically done with the 2-degree field survey, galaxy redshift survey. And there are two interesting things to note about this sliced way of looking at it. It might be difficult to pick out or not. So you might see, or you might be able to see, there are strands of galaxies moving along, or seemingly pointing towards the observer. The observer is in the center here, and these galaxies appear to be sort of pointing almost towards the observer in different places. So where there's large concentrations of galaxies, these black bits, they all seem to be pointing towards the observer, towards the Earth. And this is called the fingers of God effect. Now, it's not because there is an actual God and he's pointing us out. We're all here. No, it's actually due to an effect of the fact that not only does space expand, but you have to consider the fact that galaxies themselves will move. You know, they respond to gravity, the pull of another galaxy, etc. So what we're seeing here is these large distributions in the redshift side of things is actually down to the galaxy's own motion being imprinted onto the expansion of space itself. So because we're just measuring the expansion of space, any movement of the galaxy is also added into that. It's convolved, it's been sort of entangled into that data, that information that we're getting. So it creates this fingers of God effect. And there's another effect as well called the Quasar effect, which is kind of the opposite. You get strands of galaxies forming perpendicular, and that's just galaxies being halted and infalling towards. They're starting their infall towards these structures. That's what that kind of implies there. So another representation of this, if you can make it, I apologize if the contrast is a bit weird on this, but this is like a 3D view of that same slice, but I think it's four slices, and it quickly spins it around, and the resolution is a bit poor, but if you can make it out, might be able to make out that fingers of God effect a bit more strongly in this. If you can see the strands sort of heading towards the observer. It's a cool little movie, but it's a bit difficult to see because the resolution's a bit poor. So we've not only got our superclusters, our galaxy clusters forming this structure, I've already sort of touched on these things a little bit already, but there are also other common structures that you can find at large scales, such as sheets and walls. Another great example of this is in 1989, Margaret Geller and John Hooker being another very famous astronomer for the time. He discovered what was called the Great Wall, which is not the same as this one that is mentioned here. This is an earlier one. This Great Wall was a sheet of galaxies, and it was more than 500 million light years long and 200 million light years wide, and only 15 million light years thick. But still, it was this great chunk of galaxy, loads of galaxies in such a concentrated way, forming what looked like a wall of galaxies. However, this was superseded by the discovery with the Sloan Digital Sky Survey in the early 2000s, with the Sloan Great Wall, which is this one. And that is about 2.7 times bigger than just the Great Wall, which has about 1.37 billion light years in length. So it's even bigger structures, and it's about a few billion light years away as well from us in terms of distance. So not only are there sheets and walls, there are also filaments, which I talked about earlier. And filaments are basically where most of the galaxies will form along because they collapse along dark matter from what we model, at least. Not a lot is fully known about the origins of how things collapse and coalesce onto each other, but this is based upon what we guess, I guess, educated guess. And they form along, galaxies form along these filaments, and then these filaments are what, as I showed earlier, collapse into those large structures, galaxy clusters. And then one of the last things, I guess you won't really consider it a structure, to be honest, it's the voids, which is the great space between the galaxies. These regions here, the bits that are empty, basically, or seemingly empty. So yeah, and as mentioned, the sheer scale of these structures is just incredibly large. So you can also analyze the distribution of quasars and the most luminous objects in the universe. And again, you can sort of use these to see the distribution of your objects in the night sky. And it shows that this light is absorbed by sheets of intergalactic gas in some way. Well, there's intervening gas between the distant quasars and us that's absorbing the light. So there's not only intergalactic gas, intracluster gas, there's also interstructure gas, if you want to put it that way, I guess. So this forms what we know as the Lyman alpha forest. And also can be used to indicate the when reionization occur, which is when we get to the Big Bang, really. Well, it's not Big Bang, sorry. It's when we get to the birth of the first stars and such as that, to be able to reionize the universe again with visible light. So yeah, we cannot wind back the clock, but nature definitely uses footprint. As we know, with the cosmic microwave background, people might have seen this before. I don't want to make too much assumptions, but so this, if you don't know, the cosmic microwave background is an echo of what is now to be theorized under the Big Bang model of cosmology. Formally, that's what it's known as. It's supposed to be a footprint of the birth of the universe. But not only is it just a footprint to the fact that something happened a very long time ago which gave birth to the universe itself, but it also shows very tiny fluctuations in temperature. And these are used to sort of measure the density fluctuations in the universe. And from this, you can then infer the foreground structures that will form and grow and form the galaxy clusters, etc., against the background cosmic microwave background. So these subtle dense pockets allows for the growth of dark matter and then the accumulation of the visible matter that we see. That's that's basically described formally. The universe is then obviously modeled very heavily, and that's how we come to illustrate the things I talked about earlier in terms of the structured growth and the formation, and based upon the observational evidence of the cosmic microwave background. So simulations such as the Millennium Run, as it's formally known, which used arrays of supercomputers to test the physics of observation. So the data from the Wilson microwave anisotropy, microwave anisotropy probe compared the CMB observations to that, to be able to form the growth of the structure from the dark matter, to basically copy it, see what was on the CMB, those density fluctuations, and then map the concentrations of dark matter to those points. So yeah, you can test for the distribution of this, the dark matter, and therefore the baryons, which is the visible matter, coalesces onto the dark matter, as well as the origins and distribution of light in the universe as well. And it allows you to also constrain your cosmology models as well. So the fine-tuning problem that exists in cosmology, I'm not going to go into too much depth of that, but there's a problem in cosmology where there's a certain fine-tuning element required to be able to get the right carbon copy of our universe that we're in. It's what leads to many debates about the anthropic principle, the etc., etc. So it's very, very deeply conceptual at this point now, but I won't go into too much depth. But yes, and aside from that, this is an actual observation of a distant quasar, as I was talking about earlier, distant quasars of the intervening gas, which appears to be a gas from a galaxy filament that's just happens to be in the way, and it doesn't seem to be associated from any other objects nearby. I think the scale of this object is several megaparsecs. It's quite large for a gas cloud, so it's definitely not associated with anything galactic or extragalactic. So it's quite a massive collection of cool gas in the way. So you've got all this structure, and it appears that the universe is structured completely and utterly, as George Abel and his forefather and his prior experts in the field found. It appears there is structure, but we have to ask ourselves the question: is this structure we observe, right? Is it boundless? Does it just forever end to further and further structure? And the short answer is basically no. We enter a point where we get to certain scales, specifically 100 megaparsecs, where the universe's structuring appears to fizzle out. It becomes more homogeneous and more isotropic, and it becomes less to pick out the fine bits of detail. And this is known formally as the end of greatness, because everything has to sound extravagantly grand. But as you reach the scales of 100 megaparsecs, very large, it's like nearly a million, not a million, about 1,000 billion or so kilometers. The universe recouples with what I kind of described already, the cosmological principle. The cosmological principle states that the universe is both isotropic and homogeneous, and it applies to the laws of physics mostly, in that you expect laws of physics to be just work everywhere uniformly and behave in the same in every direction you observe the universe. But this is also true for the actual structuring and scale of the universe when you zoom out further enough, and it seems to be the case from what we can infer in the observations that the structuring does disappear and therefore leads to the end of greatness. Smooths out. So this leads on to possible future works, future things that will the astronomical community will look forward to in studying this area. There is something called the Horizon Run, which Professor Brad Gibson is heavily involved with. He might have mentioned it, he might have not. But it will be the world's largest volume of visible matter, basically being simulated in a box, in a very large box. It's the largest slice of fake galaxies being formed, if you will, in a computer simulation. It's very computationally expensive, very time expensive, but it'll be worth it to see if we can, if our understanding of cosmology and our understanding of formation of structure is true. So we'll have improved resolution on this as well, so you'll be able to zoom in to finer details of these different structure formations and see what's happening as well. So you'll be able to get better data out of that, better numbers, be able to understand those numbers better. And be able to track the production of the elements in the universe, which is very important. It's part of the building blocks which make us human and how we're here today. We wouldn't be here today without the heavier elements, as well as the primordial elements which started everything, that seeded everything to begin with. So that ultimately leads to the sheer size of this being incredible, and people will no doubt be excited and cannot wait for it to complete. It's currently running at the moment, I believe. I'm not sure when its end date is, but I believe it's in the near future, not more than a year away. So we'll be able to have some sort of exciting results then. Perhaps Brad might touch on it or not. He might not. But yes, anyway, so there we have it. That is the structure formation on a journey, the hierarchical nature of the universe. So thank you very much for that, and thank you very much for having me, and I must apologize again for technical difficulties. Any questions?
Lawrence, thank you very much. That was an incredibly interesting talk. I'm going to have to go and lie down in a dark room somewhere and think about lots of it. Could I ask you to stop sharing your screen?
Oh, yes, of course.
So, ladies and gentlemen, I'll give you a few minutes to get your questions sorted out in your minds. And then, as usual, I'd prefer you to put a digital hand up. If you don't, then just wave at the camera and I'll try and recognize you. But while people are thinking, Lawrence, your image of the bullet galaxy,
Oh, yeah.
does that indicate that the actual baryonic matter is disassociating itself from its dark matter lump? And is it a clear indication that dark matter itself lumps together? It's not uniformly spread through the universe.
Good question. Yeah, so I don't know if I probably didn't make myself clear earlier. Sort of probably thinking as I was trying to say it clearly to make sure it didn't sound too confusing. But so essentially in that bullet cluster, what's happening is you've got the smaller cluster going through the larger cluster, and then the end result is that you've got the lensed the actual concentration of the lensing is coincident or in the same place as the actual galaxies themselves, but the cluster is receding. The intercluster medium, the gas is receding behind it, because the ICM has had heavy interaction, so it's been slowed heavily. Whereas the actual galaxies themselves, they're following the bulk of the dark matter, which is uniformly distributed in that case. And dark matter does not uniformly distribute as such. It does uniformly distribute in a way from what we model, but it concentrates into pockets in these density fluctuations in the CMB. And then what we do is well, not me personally, but what the simulators do is that they focus on studying the dark matter and how the dark matter sort of collapses, and then how the visible matter will collapse with that dark matter. Because whenever they model dark matter, they always make the assumption that the visible basically follows with it. The visible matter follows along with it. The baryonic matter follows along with it. So it's uniformly distributed in clumps, in halos, but not across the universe until you zoom out far enough.
Right. Okay. So I think I understand a little more, but once again, back to the dark room and have a deep think about it. Ladies and gentlemen, I'm looking around for questions. I'm not seeing any digital hands. So Phil Moffat.
Oh, I've got one.
Okay.
As usual. I always see this matter condensing, like condensation, like moisture on a window where it forms into droplets. But my question is, when you get filaments condensing into nodules or node points, is the matter coming together along filaments and then creating galaxies, or do the galaxies form in the filaments and then come together to form these points? Because there's a vast difference between them, and I can't quite get my head around what's happening. Does that make sense?
It makes perfect sense. Yep, no worries. Yeah, so what happens is that, at least from what we model in the simulations, that the gas, so if we start from the beginning, the gas sort of collapses into the filament strands, and then the gas will eventually lead to the birth of stars and then galaxies, forming out of that. So the galaxies form first in the filaments, and then the filaments are traveling along with expansion of space, and then eventually they'll meet another filament, and then that will cause them to collapse on top of each other.
I suppose the increased mass in areas creates more gravity to pull more matter in.
Yep, that's basically the gist of it. Yep.
Okay, thanks for that, Phil.
Lovely talk, by the way.
Oh, thank you very much. Appreciate it.
Thank you, Phil. Peter Lloyd.
Can I ask you what I hope is a very simple technical question? On one of your slides, the one I think simulating the universe, there was a scale marker of 31.25 megaparsecs per H. What is the H?
So the H is it's a Hubble parameter. So what we tend to do whenever we talk about scales is that we tend to measure them with respect to the Hubble parameter, so which takes into account the expansion of the universe. So essentially, because obviously, when you consider distances in space, you have to take into account the fact that the Hubble expansion will affect things somewhat. And if you want to make your observations comparable, if you want to compare them with someone else's work, it's best to normalize them or weight them, if you will, to the used Hubble constant value, because there are some people or certain groups of people that use particular set Hubble constant values that are, they're real calculable values. It's just that they prefer using one telescope. They might use the Planck definition, for example, from the Planck telescope, or they might use one from WMAP. Different telescopes with different results. They're ever so slight, but they're between 69 and 72 or so now. But the whole point of doing that H, that Hubble parameter normalization, is just to make sure the results that we compare with are consistent. So what I do is basically comparable to what someone else does.
So perhaps at the start of that explanation, I thought, I see, yes, of course, this is the difference between the distance the object appears to be to the distance it's actually at, because it appears to be closer than it actually is because of the time it took the light to reach us.
Yeah.
It's compensating for that effect.
Basically in some way, it's compensating for the expansion of the universe, and yeah, it's basically it, what you just said, to be honest.
Okay, thank you.
No.
Okay, we've got a question from Michael Poxon, who's been particularly shy tonight. Has any mathematical study of the structure been made? Fractal dimensions, etc.
Yes, I believe, because the structure formation is sort of fractal in nature, so I think there are mathematical studies on this. I cannot tell you much about them because it's nowhere near my area of expertise, but I do know they do exist for sure. Yeah.
Presumably, Brad Gibson's mathematical model, computer model, will be doing some sort of analysis like that.
It very well could do, yeah. It very well could do. I don't think it's something they'd probably focus on, but for definitely, we've got a new member of staff starting soon who's actually probably more interested in the cosmological side of things. So perhaps they might look into it. Who knows?
Right. Okay, I'm still looking for questions. Andy Devey, can you unmute yourself, Andy?
Unmuted.
Okay.
Just a quickie. The hot gas in the interstellar medium, any further progress on to what's actually heated it up?
The hot gas. Oh, yeah. So, yes, this is interesting. So, what we currently believe is the actual gas itself is heated by galaxies when they infall. The current model is that I don't know if anyone's heard of active galactic nuclei or is familiar with them, but there is a belief that galaxies with an active nucleus, an active supermassive black hole in the center, is actually actively spewing out material and feeding the environment with some sort of hot gas as they infall inwards, and also other effects as well, such as the gas in infalling galaxies, especially newer galaxies. They help to continue to feed the hot diffuse gas, the ICM, by donating some of its own material into the hot environment through stripping and things like that. So it's mostly down to release of emission from AGN, is what it's believed. AGN feedback into the environment, as well as supernovae potentially as well. So supernovae create little bubbles of material, and they eventually feed these galaxy clusters over time with hot gas. And because they don't collide as much, these particles, they just remain hot. So until they interact with another particle, they can't cool. So yeah, it's this AGN supernova sort of model of enriching the environment.
Okay, thank you.
Okay, thank you for your question, Andy. And ladies and gents, I'm looking around for questions, and I don't see anybody else waving at me. And so I think we'll call it a night there. Can we give Lawrence a big Mexbrin Swinton thank you in our usual manner? Thank you very much, Lawrence.
Thank you. It's been an absolute pleasure.